Okay, great. So we're going back to the supermassive black holes and the low frequency gravitational wave regime. And this talk will focus on what we already know from gravitational wave limits and of course the future, which is multi-messenger. So first of all, we know from observations of nearby galaxies that every massive galaxy hosts a supermassive black hole with a mass of 1 million to 10 billion the mass of the sun. And this supermassive black hole is a very important component for the host galaxy. We also know that in the hierarchical picture of structure formation, galaxies merge often. So the natural outcome of a galaxy merger is the formation of a galaxy that has two supermassive black holes, which progressively lose energy and angular momentum, and the two black holes end up at small separations. There's a lot of uncertainties in the evolution of the two black holes in the post-merger galaxy, especially because we don't have observations at the very small separations when the two black holes are at sub-parsec separations. And of course, this is the most interesting regime because when they get at very small separations, we expect them to become strong sources of low frequency gravitational waves. And of course, this is a gravitational wave session, so you're all very excited about gravitational waves. We have gotten a lot of excitement from LIGO the last few years. The black holes, the supermassive kind, the gravitational waves cannot be detected from the ground, but they will be detected by LISA, the least massive of those, the black hole, the binaries that have 10 to the 5 to 10 to the 7. And of course, now there is ongoing effort to detect gravitational waves from the most massive of the binaries that have masses of 10 to the 7 to 10 to the 9, and they emit in the nanohertz regime. So I will talk a bit more about pulsar timing arrays, and Nicholas gave already a nice introduction. Just very briefly, pulsar timing arrays is a galactic scale gravitational wave detector that relies on pulsars, which are very stable clocks on the sky. And of course, pulsars are very stably rotating neutron stars that give rise to this lighthouse effect that you can see here. When the beam of radiation passes through our line of sight, we get this pulse of radio light, and because it's rotating very stably, we get the repetition of these pulses very coherently. So in this galactic scale detector, practically you can imagine that every line of sight to its individual pulsar is like one of the arms of the interferometer, for those of you who think about interferometers. And what practically happens is we have a galaxy merger in a distant galaxy. We have the formation of a compact binary that emits gravitational waves that propagate through the universe and eventually get through our own galaxy. And they perturb the space-time of the pulsar and the Earth. So what happens, we have a squeezing and stretching of the distance between the pulsar and the Earth. And that means that some of the pulses will arrive faster, some will arrive slower. And if we observe this effect across multiple pulsars, and they have a specific signature that is correlated, we can detect gravitational waves. And as Nicholas said, we have two main signals that we expect to detect. One is a gravitational wave background from the superposition of many signals. This is very exciting because this may happen very soon. In fact, NANOGRAV was the first one to put out a result that saw correlated noise across many pulsars, and that motivated our colleagues in PPTA and EPTA to analyze their data as well. I'm going to focus on the individual binaries, which hopefully will be detected soon after the background, but I will argue now that there is a lot of interesting science that we can do even before the first detection. So what I'm showing here is a map of the upper limits from the NANOGRAV 11-year dataset. The stars show the pulsars that we observe. And you can see that at the part of the sky that we have more pulsars, we have higher sensitivity, so we can place more informative upper limits. Of course, showing you this map and pointing at the particular part of the sky and saying that the strain upper limit is something 10 to the minus 15 doesn't say much. But if I were to tell you that in galaxy M87, we can exclude the binary with this mass ratio at these frequencies, I think that would be more intuitive. So I led one paper for NANOGRAV to practically put this map in astrophysical context. And for this, first we need to build a catalog that contains all the potential hosts of these supermassive black hole binaries. So I used an all-sky survey in the near infrared called 2MASS. And I built a catalog of 45,000 galaxies. And as you can imagine, the important quantities for these galaxies is the distance, because the gravitational wave signal depends on the distance. The more nearby the galaxy, the stronger the signal. And also the mass of the central supermassive black hole, which we can assign to the binary. And again, the more massive the binary, the stronger the signal. So now that we have this catalog, we can populate it with hypothetical binaries. In the most optimistic case for gravitational wave detection, compare it to the upper limit maps that I was showing before, and conclude that there are about 200 galaxies that are within this volume that NANOGRAV can probe. So if they had binaries in them, they would produce detectable gravitational waves. And these galaxies are shown in this map. So they're very special kind of galaxies. They're the most massive galaxies in the universe, with a black hole mass of 10 to the 9 to 10 to the 10. And for now, NANOGRAV can see only a small volume of the local universe up to 500 megaparsec. So of course, since we haven't detected again, we will use the upper limits to place constraints. So what we do is we take each of these galaxies and we run our upper limit analysis. So from the PTA data, we can place a constraint on the gravitational wave strain as a function of frequency. Then since this strain depends on the distance and the chirp mass, we have the distance from the catalog, so we can convert that to a constraint to the chirp mass, again as a function of frequency. And the chirp mass depends on the mass ratio and the total mass. We assume that we know the total mass from the mass of the central supermassive black hole, and then we can eventually convert our limits to a mass ratio upper limit, which is the bottom panel here. So the interesting finding in this work was that for our best galaxies, and best in this case means the most massive and the relatively nearby, that we can place the better constraints, we can place very informative upper limits here. So if there is a binary in this specific galaxy, the secondary black hole, the least massive, has to be 10 times less massive than the primary. And this is exciting because this is the level of constraints we can place for a binary companion to Sagittarius A star in our own galaxy. Of course, we did more in this paper. We, assuming that the mass ratio at coalescence or in the gravitational wave regime reflects the mass ratio of the parent galaxies, we can also say something about major mergers. And it was the first time we placed the constraint on the number density of major mergers based on gravitational waves alone. But in the interest of time, I will just refer you to the paper. Of course, the interesting thing is that as the array becomes more and more sensitive, these limits will be pushed down. And of course, eventually we will get to the first detection. And this will open up the possibility for multi-messenger detections, which is very exciting. And we already heard the excitement about the neutron star merger and the multi-messenger detections. So to do that, I will have to take a step back and describe how we can use electromagnetic waves to find supermassive black hole binaries. You can imagine that when the binaries get to the gravitational wave regime, they're at very small separations, and there's no telescope that has the resolution to see the two black holes in a distant galaxy. So we have to infer their presence from the effect they have on their environment. And the most promising way is to find quasars or AGN with periodic variability. The idea behind looking for AGN is that we know mergers, at least some mergers trigger AGN activity. So maybe AGN hosts two supermassive black holes. And the periodic variability, I think it's very intuitive, but it's been studied with simulations many times over. And what we typically see when we embed two supermassive black holes orbiting around each other within a gaseous disk is that the binary acts as a propeller. It expels the gas from the central region, but it also pulls streams inwards and creates these mini disks of gas that is bound to the black hole and is moving with relativistic speeds along with the binary. So I will focus on a particular signature that has to do with this, the formation of this mini disk, and that is relativistic Doppler boost. The idea here is that if we have an unequal mass binary, the secondary, the smaller black hole, we have a typically brighter mini disk, just because it moves closer to the edge of the cavity and it pulls more of the material in. And it's also the one that is moving faster. So by special relativity alone, so when this smaller and brighter black hole moves towards the observer, it will appear brighter. When it's moving away, it will appear dimmer, and it will give rise to this quasi-sinusoidal variability. As a side note, this field has seen a lot of development in the last 5 years. And with the time domain data that we have, we could look for quasars with periodic variability. That's something that I've spent a lot of my time. So if you're interested, please reach out to me. But going back to the multi-messenger aspect, the important thing here is that with time domain data, with electromagnetic observations, and with pulsar timing arrays, we can actually probe the exact same binaries. So here is the simulation of the gravitational wave, the time residuals that a supermassive black hole binary induces to a PTA like NANOGRAV. And here is the Doppler boost signature that is produced by the relativistic motion of the secondary. And you can see that the two are related. The frequency of the gravitational wave is twice the frequency of the electromagnetic wave of the orbital period of the binary. And practically, it makes sense to put the two together. And I'm working on a pipeline to combine and analyze NANOGRAV data, PTA data with time domain data. And of course, this is very interesting because there is a significant overlap in the parameters that we can do that. Here I'm showing the mass of the binary and the period and the, let's say, the areas that these signatures are detectable. So starting from a close to edge on binary to higher inclinations, this is the area that we could detect the Doppler boost. And then taking into account the sensitivity of the array, currently with NANOGRAV, the 11-year data set, which is the last that has been analyzed for individual continuous sources, continuous waves, we can only probe the most massive binaries up here, but as the sensitivity of pulsar timing arrays increases, the parameter space opens up. So within 5 years, we will have many more binaries we can probe jointly. And of course, in the horizon, 15 years, this will become even bigger. Of course, there are significant developments that we expect in the next 5 to 10 years. We do expect the first detection of a supermassive black hole binary by PTAs. And in the electromagnetic side, we expect LSST, which will be the best time domain survey to do this type of searches. So there's a lot of excitement about what we can do. And of course, this joint detection is one of the many. We wrote a white paper a couple of years ago summarizing all the potential signatures that we can put together and all the questions that we can ask. And I will just leave you with the summary and take questions because I'm sure you are eager to get to the break.
Thank you, Maria, and thank you for being on time. Questions for Maria? Nicholas, go ahead and unmute yourself.
Yep. Okay. Maria, thanks for the very nice talk. I have like a small clarification, small correction, like historical correction, and then I'll get to my question. Just to mention that you've mentioned that the other PTAs have responded to look for common background signals due to the NANOGRAV paper. That's actually just for the history is incorrect. We've been tracking common signals also since 2014. The order of the papers have to do with other things like publication policies and differences in the parameters that we are finding. But with regard to this other exciting issue with single sources that I've also worked a lot on, just to help also the audience, could you point out like what is the difference in the parameter space we can probe if we do this detection of the supermassive black hole binary only with the PTA, so only the gravitational wave, and how this parameter space improves either in number or in quality if we have a joint, PTA and electromagnetic counterpart observation?
Okay, so I just showed the common parameter space. The question you're asking is not answered yet. So we are building the pipeline, so I cannot tell you how much we improve the parameters. We know that if we use electromagnetic information to inform the gravitational wave search, we already gain sensitivity. For example, just by knowing which position to search for, we gain a factor of 2 or more sensitivity. If we add information about the period, we increase again, we can constrain the parameters better. The idea here is just to put agnostically, put the two signals together because it's the same binary we can probe with two different methods. So for me, it's a no-brainer that we will put the two data sets together. But practically the improvements are yet to be seen.
Can I follow up, please, Vasiliki?
Please go ahead.
Okay, so with regards to the mass, how much can we actually understand? Can we probe more than the chirp mass in terms of like individual masses for the supermassive components?
So there are, I will have to get into the details of the model now. So with that's the promise of combining the data, that you can probe different things with different signals. So as you said, the gravitational wave signal, we can probe the chirp mass. Now, if I go to the electromagnetic signal, the Doppler boost, that doesn't depend on the chirp mass the same way that the gravitational wave depends. So the promise here is we will be able to break some of the degeneracies that we would have if we had the gravitational wave signal alone, just because we add more information from the light curve. So here, the amplitude will depend on the mass ratio, the total mass, and the inclination. So there are common parameters, but the dependence is very different.
Okay, we also have a question in the chat. Konstantinos Markakis asks, at which wavelengths do we expect the clear electromagnetic signatures? Shouldn't binaries be found in dusty and therefore obscured environments?
I don't think it's necessary. I will just say that the focus of the past years has been driven by the availability of data. So the 150 candidates that we now have are from optical time domain surveys, because these have been the most systematic. But we have explored this Doppler boost signature both in optical and UV data. We do expect that there will be X-ray luminosity from the innermost of these mini disks, so X-rays could also be promising to look, but the data are not that great.